Absolutely. So we go from having a CH2, because I've got a carbon explicitly shown 2 bonds, so there must be 2 more hydrogens, to a CH3. So I have added a hydrogen. It was not there. Now, to be fair, I'm trying to give you guys exposure here. I didn't even mean to add this. I'm not trying to focus right now on the chemical reagents, just on the chemical change. I want you to get comfortable spotting the difference, recognizing what change has happened. CH2 to CH3, carbon to carbon OH. So I have added an H and an OH. Did my H add to the carbon with more hydrogen, the less substituted carbon? It did. I had a carbon with no hydrogen and a carbon with 2 hydrogens. Carbon with more hydrogen is where the hydrogen added. So we would describe this reaction as following Markovnikov's rule. This is a Markovnikov addition reaction. What about the reaction below it? Is it addition, elimination, or substitution? Addition. What did you notice about the reaction that helped you confirm that? An alcohol is added. I think I heard somebody else say something. Pi bond is consumed. I have a pi bond in the starting material. My pi bond has been used. Those 2 atoms that are no longer bonded to each other twice, they're now bonded to new groups. Is hydrogen one of the groups that's added here? Addition should add 2 groups. Is hydrogen one of them? If we're not sure, then we should draw in the assumed hydrogens, right? So that we can feel confident. Are there any hydrogens up here attached to this carbon? How about down here? 1 attached down here. That hydrogen still present here. Now it's a wedged hydrogen instead of flat. And what about here? There is 1. So I went from having no hydrogens to 1 hydrogen and having just H to H and OH. Okay, so I had addition, which means I should have 2 groups added. One of them was a hydrogen. The other, again, was an OH. Both of these are considered hydration reactions because we add an equivalence of water. I added H and OH, H and OH across the pi bond. Was this also a Markovnikov addition? Which carbon did the hydrogen add to? Did it add to the carbon with more hydrogen, or did it add to the carbon with less hydrogen? The hydrogen added to the carbon with less hydrogen, which is opposite of Markovnikov's rule, so we call it anti-Markovnikov addition. Walk it out for me. Work it out. Walk it out. I think I meant to say walk through it. Markovnikov's rule says? Correct. Correct. Yep. So this had more hydrogen, and this is not where the hydrogen added. This is where the OH group added. The hydrogen added to the carbon with less hydrogen, which goes against Markovnikov's rule. Seeing how to apply it? It was added to the carbon that had more hydrogen. So Markovnikov and Zaitsev were kind of contemporaries. They lived around the same time. Markovnikov had his PhD first and actually made some waves saying Zaitsev's rule should not what we call Zaitsev's rule, which Zaitsev was working on to get his PhD. Markovnikov said Zaitsev's idea doesn't make any sense and he shouldn't earn his PhD for the work he's done. Meanwhile, Zaitsev's rule actually makes a lot of sense, and we'll get into that when we get into elimination reactions in Unit 5. Markovnikov's rule makes no sense. It is unfounded. His rule is based on hydrogen. It has nothing to do with the hydrogens. It's just a coincidental thing. So I love that for the sake of like international ancient gossip. Markovnikov had a worse idea, but he was the one trying to shit on Zaitsev's idea. Cool.
When you say like less, the carbon less or more, are you talking like for the top one, you're talking about CH2 and then the one that the other carbon that's double bonded?
Well, the two carbons of the alkene, the two carbons that go through the addition reaction.
Okay.
I think we can agree these methyl groups don't go through any change. Yeah? So I'm not paying attention to whether a hydrogen was added or not there, because they're not going through any change. So you're right, I'm paying attention just to the two carbons of my alkene. We will see some reactions where another carbon in the structure is involved as well, and it involves rearrangements during the reaction intermediate. We'll get into that later though. All right, I'm gonna erase the hydrogens I added here that helped us prove that this was anti-Markovnikov. Now I want you to decide whether this reaction is a syn addition or anti-addition reaction. Syn addition means adds to the same face. What adds to the same face? The two groups. Addition reactions add two groups. Syn addition should add two groups to the same face. Anti-addition adds two groups to opposite faces. What do we see here? Does my reaction add my two groups to the same face, syn, or does it add them to different faces, anti? Because you're seeing the methyl group wedged and the OH dashed. Was the methyl group one of the groups added? The methyl group was present. A hydrogen was added at that carbon. So what are the two groups that added? H and OH. It is syn. These added to the same face. This is a syn addition reaction. Of the molecule? Well, the carbons have to be on the same side of the molecule. If they're a part of an alkene, they have to be bonded to each other. If I had rotated this so my pi bond was like on top, would that have thrown you for more of a loop? Like, I don't know whether this is the left and this is the right. Now it's anti. Just rotating it. I'm glad you said that though. We're not looking at sides of the molecule. We're actually looking at faces. Remember, first, let's recall the hybridization of these carbons. SP, SP2, or SP3? SP2 for our alkene carbons, because they only have 3 electron regions, spp. What geometry does that have? Molecular geometry. Trigonoplanar, aka flat. These are flat atoms. So if we looked at this on its side, it looks like this. This is all in the plane we're looking at, and then this all goes away from us. So what we're saying is that the H and the OH, oops, that was where my H adds. They actually both add down onto the same face. They add onto the bottom side of those flat carbons, rather than one adding to the top face and one adding to the bottom face. Direction in space? Sure. On a ring, syn addition will mean they're both down or they're both up. Not necessarily that they'll be axial or equatorial. That we can figure out in the chair conformations. But like we had cis and trans to describe groups on rings, that's what we're saying here. My H and OH are cis to each other. So they must have been added by syn addition. No. Now remember, cis and trans can only be used on rings and only on di-substituted rings. As soon as I have more than 2 groups, I can't describe them all with cis or trans. I can only describe 2 things. And the reason I can do that on a ring is because the ring is locked. It's not allowed to rotate as much as it wants. It can either rotate a little bit, axial and equatorial, and then the other way, axial and equatorial, but it can't rotate all the way around. Linear structures are allowed to rotate all the way around, which means that this is just one conformation of my molecule. And when you look at it, it looks like we could describe it as cis because the 2 groups are both wedged, but we can't describe it as cis because it's not a ring, it's linear. I can draw a conformation of this molecule. Remember, I go from zigzag into zig-zig, and my absolute configuration is not going to change at this carbon, but the way that it's oriented in space does change as I start to rotate around that bond. So this chlorine group is pointed towards you. As I rotate around that bond and I get into zig-zig, now the chlorine group is rotated away. You guys remember working with the models? When we had that activity where you twisted it, drew it out, twisted it, drew it out. This looks cis. This looks trans. They're the same molecule. So which one is it? Cis or trans? Neither. I'm not allowed to use that kind of language on linear structures. Yet, this reaction is either syn addition, they add to the same face of the flat alkenes, or it's anti-addition, they add to opposite faces of the flat alkene. This is something we'll talk about more next week, but alkenes are not allowed to rotate around their pi bond. It breaks the pi bond by doing that. So this pi bond reacts in this zig-zig configuration. This pi bond is not zigzag. That would be a stereoisomer. This pi bond is zig-zig, which means the way that it reacts will produce a product that keeps that bond line in its zig-zig configuration. And what we can see here is the chlorines have added to opposite faces. One added wedged, one added dash. That's the top face of this flat alkene and the bottom face of the flat alkene. But that's a high energy conformation of the molecule. If you have a zig-zig conformation, it's always eclipsed. And eclipsed is always high energy, the pinnacle of those energy states. So this molecule forms like this, and then it just quickly rotates into a lower energy conformation. So we name these reactions based on the way they form, not in the way that they take up the lowest energy. So this reaction is anti-addition. We're going to be coming back to this a lot. So this is not meant to help you feel super confident in what all this means, but when we come back to it over and over, this is your foundation. I'm showing you that it can be challenging. Markovnikov or anti-Markovnikov addition? Neither. Hydrogen is not involved in addition across the pi bond. So Markovnikov screwed himself because half of our addition reactions don't even apply to his rule. All right. What type of reaction do we see here? Elimination. How do you know that? We form a pi bond. I wouldn't say a pi bond is added because I don't want you to think about addition, but we form a pi bond. A pi bond is left over in the product of this reaction. which means I have eliminated 2 groups to allow those 2 carbons to bond back to each other. Oh, but I guess I didn't really give this to you. So we're going to use Zaitsev or Hofmann here, Zaitsev or anti-Zaitsev. All I gave you was that Zaitsev forms the more stable, the more substituted alkene. Hofmann goes for the less stable, less substituted. There was another option for an alkene to form here. That is, my alkene could have formed between the 2 more substituted carbons, but instead my alkene formed between a less substituted carbon, which means my alkene in general is less substituted. So this is anti-Zaitsev, aka Hofmann. I wanted to give you guys some context for these terminologies. I think I just gave you so much time yesterday looking at all of them, writing down stuff. I wanted you to be able to have some examples in your notes to apply them, but we're going to come back to them. This is not the end of this discussion, just the beginning. Jordan and then Annie. Great question. It's an abbreviation for a tosylate group. It's toluene sulfonic acid or toluene sulfonate. This is the O of OTS, and this is the TS. Pick your poison. I like OTS better. Yeah.
When we see the product for that example, and we see like the alkene forms on the end there, like in going about figuring out what it is, do we just say, okay, it formed here, but it also could have formed here, and this one is less substituted than this one, so that's just kind of how we reason it?
That's exactly right. So we will talk about this in Unit 5. But this is what we describe as a leaving group. Obviously, you can see that it has left the molecule. It's not there in the product. In order to form an alkene, this carbon has to have a leaving group, and one of the other carbons around it also needs to have something leave. One of its hydrogens will need to leave. Here is a more substituted carbon. What degree of substitution is this carbon? Secondary. On the left is a less substituted carbon. What degree do we have here? Primary. I've formed an alkene with the primary carbon, the less substituted carbon, rather than the secondary. Therefore, my alkene is also less substituted than it could have been. We'll talk about degrees of substitution on alkenes next week as well. So this will all make a lot more sense. I know it's going to feel a little confusing. I wanted you to see some of it applied. Okay. I want to talk a little bit about solvents because I know you'll be coming across solvents all the time. There are 3 major groups for solvents. We have nonpolar solvents. We have polar aprotic solvents, and we have polar protic. I think you can see here that protic and aprotic are related to each other. But what are they describing? What do you think that term protic implies? Nice. Protic, meaning has protons available. And a proton, of course, is the hydrogen nuclei. Protic means proton donor. So aprotic would be non-proton donor. Well, proton donor, that's the terminology we use to describe acids. And this is not necessarily implying that we have acids, but we certainly have more acidic compounds, more acidic than our other solvents. What I would like to do is give you guys a list of some of the common solvents and have you try to place them in their category. I know there's a lot of names up here. What I would recommend is don't copy these down and then try to place them. I would recommend copying them down where you think they belong. And if you're not sure where they belong, talk with your classmates, talk with each other, and then we'll put them all down at the end if you don't get them. Also, I'm trying to think if there's any I missed. Sorry. Yeah, here's one that you guys have used and will use. Remember Lagroin? You guys used Lagroin in the recrystallization lab? That's okay. You don't, this is maybe supported by being in the lab, but not, you don't use half of these in the lab either. Wake up. I know. Gotta keep you on your toes. You saw it coming. You could stand up. Is it helping? Interesting. Let me ask you where you think the protic part is on DMF. The carbon to hydrogen?
Yeah. Oh no, that's
because these all have carbon to hydrogens as well. Mm.
So would be.
Well, I think it has a. I think you were right in classifying it as polar. It's got a strong dipole toward the oxygen, toward the nitrogen.
So would it still give up this hydrogen?
Not really, because that carbon doesn't like to give up hydrogen very much.
So even though it wouldn't give that up, it would still be.
It would be polar aprotic. And then I want to ask you about your tetrachloromethane. What kind of polarity do you think it has? Yeah, tetrahedral, everything in the same order, all polar bonds, but no molecular dipole. Good work. Did I give it away? Good. Good, good. That answer makes sense to you then. Good. What do you think?
We got hexane and non-polar.
Good. Now let me ask you why you think acetone is polar aprotic. No hydrogens, or no one that's good at giving up a hydrogen?
Because I always want to keep that.
Because it definitely has hydrogens, right? Acetone has 6 hydrogens. But O can give up a hydrogen fairly well. Oxygen's not a bad acid. But carbon,
Yeah.
not a good acid. Carbon does not like to give up hydrogens. So, polar for sure, not good at giving up its hydrogen. Perfect.
Okay, slay.
Keep that thought process going. What do you guys think? Where do you think the acidic hydrogen is in DMF?
This one?
Attached to carbon?
Oh. Okay, so it's that one.
I think so.
You know.
Because
Okay, that makes
carbon's not
sense.
going to give up a hydrogen very
Okay,
well.
okay, yeah.
I think that was probably your reasoning here
Yeah.
too. Is
Yeah.
And then what about tetrachloromethane? What do you think its polarity is like?
Oh. Probably not more,
Why?
because it's
Carbon to chlorine is a polar bond. What happens when you have 4
it's all equal.
polar bonds in the shape of a tetrahedral? They all cancel each other out. You guys ready? Yeah.
Because the O is really electronegative. It doesn't want to give away the hydrogen, right?
Actually, it's the opposite. Oxygen is more willing to give away its hydrogen because that means taking the electrons for itself. So oxygen is more likely. Yeah.
Rather than just giving it away.
Yeah, we sometimes do say like H plus just drifts away
Right.
and the O now has a negative charge. But in general, yeah, there is something else that's grabbing onto it.
Because it basically forms water, right? Or a lot of times it does. Because it,
With what?
I don't know, I guess like if there's another reaction, like it'll. I guess like
Even
ions
water.
are always like they're synthetic water.
Dehydrogenase, right? Or no, dehydrate. Yeah. There are a lot of chemical processes in the body that produce water. When you get into OCHEM 2, you'll see a bunch of dehydration reactions as well.
Okay, so it's.
But that doesn't necessarily have to do with whether it's a good proton donor or proton acceptor. Even when you think about water self-ionizes. H2O and H2O become OH minus and H3O plus, which means water is both good at taking a hydrogen and good at giving it away. But carbon does not self-ionize. Methane doesn't form CH5 plus, and that doesn't that breaks the octet rule anyways. Right? So oxygen is more willing to let go of a hydrogen because it is more willing to take on a negative charge, keep the electrons for itself.
Then infer me that alcohols are more likely to be polar acidic for that reason.
Absolutely.
Okay.
Exactly for that reason. No.
You said it can accept and take.
Yep. And so if it can accept, or if it can donate electrons, accept and take are the same. If it can donate a proton, then that makes it polar protic. The idea that it can also take a proton doesn't make it aprotic. It doesn't cancel out the ability of it to donate. All right, should we organize them? Hexane. Maybe you saw this. I was in my head just like going through the chemicals in the order I was expecting, so they're already kind of grouped. Where does hexane go? Non-polar. What about tetrachloromethane? Why? It has polar bonds. It only has polar bonds. It's entirely symmetrical. So that tetrahedral does not have a more positive region and a more negative region. It is all more negative, so essentially electrostatically neutral. What other nonpolar compound was on my list? Legroin, or petroleum ether, which is oftentimes actually a mixture of pentane isomers. This is 2-methylbutane, which is an isomer of pentane. And that's because they all have similar boiling points, similar molecular masses. They distill at the same time. Any other non-polar solvents? That's it. Did you have one, Layla, that you thought? But diethyl ether has dipoles pointing towards the oxygen, which will sum together to a large molecular dipole. Does diethyl ether have any proton donors? Is it protic? Are you saying there are no protons on diethyl ether? Because I see 10 protons, 10 hydrogens, right? Why are we calling it aprotic? Carbon is not good at giving those protons away. Carbon is not a proton donor. So diethyl ether, polar aprotic. By the way, sometimes we see this written as ET2O. I don't really like that abbreviation. I don't like putting the oxygen that's sandwiched between ethers on the outside, but you do see this sometimes. What else should go in polar aprotic? DMF. Again, there are 7 protons here, 3, 6, 7, all of which are attached to a carbon. It rhymed. It made sense. So you might also say nitrogen can be considered protic. Nitrogen is more acidic than carbon, but the nitrogen here doesn't have any hydrogens attached to it. So you wouldn't be able to try and justify that even if you wanted to. What else? Acetone. I've seen acetone abbreviated sometimes as, well, I guess let's talk about the way that we talked about abbreviating ketones earlier in the semester. CH3CO, CH3, and putting that O in parentheses is meant to inform you that it's only bonded to the carbon on the left and that it's not a part of an ether structure like this. There are some weird ways that I've seen to write it. I think maybe like CH32CO. I don't like that abbreviation. Anything else? Ethyl acetate. There is another abbreviation for ethyl acetate. Acetate, or anything that has the acete group. This is a 2-carbon carbonyl, gets acete, can be abbreviated with AC. And then to represent that there's an O, we put O, and to represent the ethyl, we say ET. So this is an abbreviation for ethyl acetate. And because it doesn't matter how you draw a structure, it doesn't matter how you write its name either, we can also write this as ETOAC. The ethyl is attached to the O, and the O is attached to the 2-carbon carbonyl. What other solvent that I gave you can use that AC abbreviation? Acetic acid. And you can see that similarity. Acete, acete. In fact, acetone even has that same abbreviation, a 2-carbon carbonyl on either side, which makes it a 2-carbon carbonyl ketone, acetone. I just talked with my OChem 2 class about this last night, so if you want to hear me whine more about it, you can watch that recording on YouTube. Okay, so if I wanted to write acetic acid, which is polar protic, because I have OH, I can write acetic acid as ACOH. Notice how I've swapped ethyl on acetic or ethyl acetate for just a hydrogen. So instead of having OET, I've got OH. And then in that same way, I can write it the other way. I can write this as OHAC, just for fun. I say that because there's no wrong, there's no one way, there's no right way to communicate these abbreviations. You want to see something most people don't like to see? That's not an incorrect way to communicate water. OH2. I almost said there are no wrong ways to communicate it. There's definitely wrong ways. Like if you put O2H, that's not the chemical formula of water. But OH2 is the same as H2O. And you will see it flipped from time to time. I want you to be comfortable with all these different ways of abbreviating it. Okay, what else? Methanol, polar protic. And methanol, we can abbreviate it as MEOH, or again, we can flip that. Oops. Home. And why am I using ME there? Methyl, ME. Water goes in my polar protic solvent, and ethanol goes in my polar protic solvent. Hoyt. Okay, any others that I missed? No. This is non-comprehensive. There are so many solvents out there. These are just a lot of the more common ones. I do want to remind you that you will not, oh, I did forget one. So let's test you on how you can rank these now. This is one that I think you will see on active. They'll list this a lot. They call it THF, which stands for tetrahydrofuran. And it is an oxygen 5-membered ring. Oxygen containing 5-membered ring. Vivi, what does it remind you of? Which of the other solvents is it the most similar to? Not quite. DMF, are you saying DMF or the one above it? Yeah, DMF was dimethylformamide. So it had an aldehyde and a nitrogen. But this looks like diethyl ether because it's got an ether functionality in it. Polar, aprotic. THF is fairly inexpensive, easy to use. But if we were running it, we'd probably use diethyl ether instead. And if you're curious where those 4 hydrogens come from that get added on to furane, this is furane. And if I add a hydrogen at each of the 4 positions, I get tetrahydrofurane. We love names that mean nothing, like furane. What does furane mean? I don't know. All right. Fun? Great. Yeah. There's not a lot of non-polar solvents, to be honest. Hexane is by far the most common. And to be honest, there's two types of hexane. You can purchase hexane, which is very expensive, or you can purchase hexanes, the S at the end, which is much cheaper. Because hexanes is a mixture of C6H14 isomers, all that have just very similar boiling points. Hexane is pure N-hexane, straight chain, no isomerism. So hexanes is cheap, readily available, a mixture of different structural isomers. Hexane is more expensive because it's just one pure compound. There's one last thing I wanted to add about this, and that is the polar protic solvents. These often run solvolysis. What does that mean? The olysis part means reaction. You maybe have heard of hydrolysis. I can't think of anything else right now off the top of my head that you maybe have heard of. Later in the semester, we're going to learn about ozonolysis. Can you think of anything else that ends with olysis? Acetolysis, is that a biology reaction? Did you just make it up? Okay, acetolysis. Probably involves some sort of acetyl group. So this olysis part just means reaction. And what do you think the solve part means? Solvent. So this is a reaction with the solvent. This is a solvent. I don't have a word. A solvent involved reaction. The solvent is a reagent. We will, in fact, run a lot of reactions with methanol, ethanol, and water. We won't so often use acetic acid, but it's not uncommon for people to use acetic acid as a solvent and as a chemical reagent. No, a reagent will go through a chemical change. Bonds will break, bonds will form. For instance, we will use water in addition reactions, methanol and ethanol in addition reactions, water, alcohols in substitution reactions. And we can do that just using it as a solvent. Maybe what I should answer is, what does solvent mean? What do you think solvent means? The thing that dissolves, the thing that's there to a larger quantity. Typically, we use a solvent to dissolve everything, get it into a liquid state so that things can move around more easily and run into each other to react. One of the things they'll react with are molecules of solvent. If I use something polar aprotic, Britton, it will not be involved in the reaction. It will have intermolecular forces that keep my reagents dissolved and suspended, but it will not go through a chemical change. No bonds will form or break with my solvent molecules. Solvolysis reactions take solvent molecules and involve them in the making and breaking of bonds. Does that feel to answer your question? Okay. Let's get into the back side of our sheet, which is on the logistics of mechanisms, the best part. How many of you have seen a reaction coordinate diagram before? Like what you see at the top of, well, this page, it's not really filled in, but a reaction coordinate diagram where you see how the energy changes over the course of a chemical reaction. Say, for instance, I'll put reaction coordinate on my x-axis. This is just saying, what about my reaction am I looking at? Products, starting material, things in between. And on the y-axis, I'll report energy of some type. Sometimes Gibbs free energy, sometimes enthalpy, sometimes just E. And then I'll see how the energy changes over the course of a chemical reaction. You've seen something like this, right? What this says is what you start with and what you end up with, starting material and products, might not be the only chemicals that are involved in this reaction. There are things that form along the way. After certain bonds have broken and certain bonds have formed, after your starting material, before your product. For example, if I'm getting dressed in the morning, I took a picture of myself out of bed in my PJs, and then I take a picture of myself out the door with my work clothes on. There was a process in which the PJs had to come off, the socks had to go on, the shoes had to go on, and those couldn't all happen at once. They had to go in a certain order. The PJs had to come off first. I can't take my PJs off if my shoes are on. My socks had to go on before my shoes because I can't get my socks on if I put my shoes on before my socks. There's a logistical sequence. There's a mechanism of how these things have to change in order for me to go from being in bed to being out the door. And the same thing is true in our chemical reactions. Certain bonds need to form, certain bonds need to break, and they need to break and form in a specific order. Otherwise, they don't work. It's not up to us to guess anymore what that order is. People have worked for a very long time to figure out what is the order of bond breaking and bond making that actually allows these reactions to proceed. It's our job to learn those mechanisms and reproduce them. One thing that has really helped with mechanistic studies are the instruments that we've learned about. If I have a starting material and a product, I can actually run data analysis during a chemical reaction, and I can get information about how things are changing during that time. A few things to point out in this reaction coordinate diagram. I've got these pinnacles, these tipping points. These should remind you a bit of our Newman projection. When I've got an eclipsed conformation, I've got something very high energy. It's not going to stay there. It's going to tip one way or the other. We call these transition states. This is where bonds are actively forming or breaking. In other words, if a bond is breaking at this point, no, it's not. It could be forming. Don't know which way it's going. At these transition states, my pen is not falling forward or backwards. There's no way to know what's happening. At these transition states, the chemical species could return to what it was before, or it could transition into something new. This is all just based on how is it being run into by the solvent molecules and the other reagent molecules. What kind of energy does it have? We'll often report transition states in brackets and give it this little symbol on the top right side called a double dagger. And to represent bonds forming and breaking, we use dotted lines. The dotted line is not a bond that is being formed. It is not a bond that is being broken. It is something in between. There is no way that you could know what is happening. Is X forming a bond to carbon, or is X breaking a bond to carbon? Yes. It's doing one of those two things, but there's no way to know what is happening. It could go either way. In these little valleys, we have reactive intermediates. I'm going to put reactive in parentheses because we don't always refer to these as reactive intermediates. A lot of times we'll just refer to them as intermediates. But the term reactive intermediate implies something useful. It implies it's not stable. It's not done reacting. It's a high energy species that is going to continue making or breaking bonds. These are things that are not the starting material and not the product, but formed in between these two. This is me not in my PJs, not in my work clothes. This is me with my socks on, but not my shoes. My analogy makes sense? I think I have used a different analogy every semester. I used to give an analogy about getting from school to home and stopping at Smith's on my way home and shopping. There's no way that I can be at home and then go to Smith's. I have to go to Smith's first and then home. But I think the clothes analogy makes sense because it really has to be in a sequence. I have many times gone home and then left to go shopping again. This is that overview. Now, we add to this the mechanism. Sometimes this is referred to as the electron arrow pushing mechanism. No, we'll add to this. This we call the reaction coordinate diagram. We'll add to the reaction coordinate diagram the electron arrow pushing mechanism. How do the bonds break? How do the bonds form? When do they form? Where do the electrons come from? Where do the electrons go? What does mechanism mean? I want you to have a grasp on that because it's not too challenging, and maybe it'll make more sense why we do what we do afterwards. What does mechanism mean? What is it related to? No right answer here, just tell me what you think. How things work. The process. You guys have taken your car to the mechanic before? I grew up as a mechanic. My dad owns a mechanic shop. I'm not a mechanic. But in theory, mechanics know how things work. You need new brakes. They know how the brakes work, so they know how to fix the brakes. They know the mechanics of your car, how the car works. You guys are mechanics. You're going to become mechanics of organic reactions. You know how they work, and you know how to show how they work. That's our goal. And if you're not happy about that, get ready for the final, because I'm assessing you on your ability to be a mechanic. Okay, so all of the skills that we've developed on arrow pushing, they come back here. We're going to talk about how to use arrows to show how things are changing in chemical reactions. I want to lay out the different types of arrows because I feel like I should have done a better job of this earlier in the semester, and I think now is a good time to revisit it. We have two categories of arrows. The first is called straight arrows. These are things like a reaction arrow. It shows A transforming into B. We have equilibrium arrows, which show A forming into B, but also B forming into A. Dynamic equilibrium. We have resonance arrows. Some of you might have seen on your exam, you had a question where I asked you to redraw resonance form A, redraw resonance form C, relate them using curved arrows. And some of you drew a reaction arrow between resonance forms A and C, and I just added the other end to that arrow because a resonance arrow is double-headed. It describes a different relationship than a one-directional arrow. Resonance means neither of these exist. They're both representations of the same thing. But a reaction arrow says this is something different than this. Other than straight arrows, of course, we'd have curved arrows. And there's really just two types of curved arrows. This is a double-headed curved arrow. Which represents two electrons. In the same way that you have become familiar with looking at a bond line structure and saying a line is two electrons, I want you to look at this arrow, which is not very pretty, so I'm going to try to make it prettier. I want you to look at this arrow, which has two hooks on it, which is what I'm calling here is double-headed. Double-headed might not be the right term. Sorry. But two hooks is representing two electrons involved. Another word that we can give here is heterolytic. No, maybe that's not the right term. I think I'll come back to tell you when that term is better. The other type of arrow is a fish hook arrow. It does not have two hooks on the end. What else could it mean if not two electrons? One electron. One electron is a radical. So these represent radical reactions. Oftentimes we use double-headed in heterolytic cleavage. That means two atoms share a bond. One of the atoms keeps the electrons. The other atom loses them. Heterolytic. Two different things happening. One atom loses the electrons, one atom uses them. Fishhook arrows are often used in homolytic cleavage. Two electrons between two atoms. One atom takes one, the other takes the other. Each atom is taking one electron. They're both doing the same thing, homolytic cleavage. We will get some practice problems today using arrows. What I want you guys to try and do is work on this reaction coordinate diagram at the top. I'm not sure what happened with my lines. So what I want you guys to do is add some lines here. It should look actually pretty much exactly like this. You have three transition states. I want you to draw a line from the starting material up to each of those transition states, down to where the intermediate box is, up to transition state 3, down to where intermediate 4 is. Then beneath it, you see all of these structures. Some of these structures are transition states. Some of them are intermediates. And I just want you to put in the circle beneath the structure where it belongs in the reaction coordinate diagram. I essentially want you to map these structures to their place in the reaction coordinate diagram. You have to use some deductive reasoning. I want you guys to take your break and work on this until about 6:20. At 6:20, we'll go through the answers for this, and then we'll move on to mechanisms. Yeah, let's go get it.
Figured it out. I don't need you anymore. Don't even talk to me.
Oh, brother. Okay.
This is what I did.
Wait, let me figure out first.
Okay. Alright. Yeah, don't talk to me. This is the next homework.
But we'll do the transition.
I was flying from him.
Right. Okay. Whatever it is, I think you got it. Cause I don't. Okay. And then it would go to intermediate this. Okay. And then it would go to this. That's what I put. Those. The rest is history. Okay. I guess I'll use my next one. Okay. Wait, I have to also do this. Wait, I thought did he literally listen to on a run first of all. And he's like, hey, so I go to York City. This is just my friend, by the way. But like we haven't talked in forever. Anyways, and I was like, yeah, I'm pretty sure that literally just talked about that like and he was like, yeah, sorry. And I was like, bye, I was like on social media, so I don't know. And he's like, yeah, I sent her with my Why are you still talking to him though? I was like, I haven't talked to him in weeks. So you were supposed to. Whatever. And he was like, how's it going? I was like, just asking about life. And I was like, oh, so I didn't ask me about the girl. And I was like, yeah, I didn't know. Then he was like, oh, I was talking to her. And I was like, okay, why are you telling me this? I didn't say that. I was like, oh, she has a boyfriend now. So, and he was like, yeah. And then he was like, I was like, you, I have to go back to class. And he was like, okay, well, maybe you can call me after, but also I might be on a date. And I was like, okay. And he was like, yeah, I might start dating this girl soon. I was like, so why are you telling me this? I'm so confused. Thank you, guys. This guy's a little bit, but it's okay. You're not gonna respond to your
Say intermediate stuff going. Good job on your.
He's literally breadcrumbing you. He is. He's trying to get back into your life. He's just testing the waters right now. You're letting it.
Good. So you guys recognize that odd numbers are transition states?
He's literally playing right in front of your face, like, I'm gonna go on a date.
Even numbers are the intermediate.
That's my son, he gets me. So then it became so complicated because his friend liked me. So then his friend was mad at us. As a friend. Are we really but now, like, not, we haven't seen each other in like, but he like goes, like he literally like, well, and I'm also pretty real, I'm like, I'm not gonna reach out. But I didn't reach out. He reached out. You're still letting it happen. I could have just not. This is true. No. I could just not. But here we are. It's fine. Let's do homework. No, I don't think we've learned this yet. So. Oh. What is it? Gotta draw.
I need to form, see out, I need to break.
The intermediate.
And here's the transition state that.
It's not keys that would generate this category. So maybe we have.
That transition state is right in the middle of it.
Fraction takes no.
How do you guys feel?
Diesel like the other ones, no.
You're
I never really liked
These
it.
ones have.
Oh, so he's just. He invited me and half friends, and like you invited me over. Yeah, like it literally like and then it like yeah. And then but then Ty got mad that it happened. So then I was like, oh, you can know this is okay. Because apparently Ty liked me more, and I was like, well, I didn't know that. No. Okay, so everyone was just spraying. Yeah. Apparently Ty didn't understand that. But he's the one who is so this is I think we're kind of like Ross the Fed.
How'd you guys do?
Good.
Yeah? Feel pretty confident on it?
Well, I don't know, but we did do it.
You did do it.
Answers.
No, they look great.
Oh, they do?
Yep, good job.
Okay. Well, I'll ask when you go through maybe. But I'm just confused where like why is there no
Not involved. Your first structure to your first intermediate.
Oh, this is just becoming something.
This is just breaking.
Okay.
So in your first transition state,
Doesn't this mean not breaking or forming? It's
well, yeah, because if it's here,
it's,
what if it falls backwards?
oh, okay.
That means the bond is forming.
Okay.
But if it falls forward, then it breaks. So your first intermediate, the water wasn't involved.
Okay.
Just the carbon chlorine bond broke.
Okay. This is like what causes that
Energy.
from just the two being next to each other, like the
Well, the bond breaking, yes, actually the water does support this process of the carbon losing its bond to chlorine, because the polar protic solvent has a partial negative that it can offer to the carbon as it takes on a positive charge.
Okay.
But a lot of times you need to add energy to this. That's going to provide the energy for the carbon bond to
like
break.
heat or like
Yep. Put it on a hot plate, put it in a heating mantle. Light does do a lot of chemical reactions. We'll use H nu to represent light. But essentially, you need to push that molecule fast enough that it can run into something and that bond, as a result, breaks off. All right, let's go through our answers, shall we? So we started, can somebody name that compound that we started with? What's our starting material here? Water is correct. And it is ethyl. No, good try. Chloro is going to come first alphabetically before methyl. 2-chloro, 2-methyl. Propane. Sorry, it's not ethane. The longest carbon chain is 3 carbons long. 2-chloro, 2-methyl propane. And our product, we can also call this tert-butyl chloride, which is not a systematic name, it's a functional class name. But you can see it's a tert-butyl group connected to chlorine. Tert-butyl chloride, tert-butyl alcohol, 2-chloro, 2-methyl propane, 2-methyl, 2-propanol.
So if you were to ask us on the test, either correct.
Correct. Either would be correct. What's the first thing that we see happen in this mechanism? Yeah, the first thing is that the carbon-chlorine bond breaks, and the water is not involved in this bond breaking or bond making at all. So our transition state shows the carbon-chlorine bond breaking. I know yours doesn't have water there. That's because water's not going through the change. It's just kind of sitting there. And then we get a reactive intermediate. Now this is a reactive intermediate because carbon has lost its electrons. It now wants electrons back. So it's more stable than the transition state, but it is less stable than the starting material of the product. It's a reactive intermediate. What's the next thing that happens? The water bonds to the carbon. And again, chloride might not be shown there because it's not really a part of this, but now a bond is forming between carbon and oxygen. And that gets me down to my last intermediate. This is a protonated alcohol. I have water attached to a carbon. Does that obey the octet rule? Why does oxygen have a positive charge? Is it lacking in octet? No. It just has 3 bonds. And oxygen with 3 bonds takes on that positive charge. It would like more electrons for itself. And in order to get to my final product, I need to break one of the OH bonds. I also need to form an HCl bond. So my last intermediate, by far the more complicated of the intermediates, has an OH bond breaking and an HCl bond forming all at the same time. All of that is happening at once. That gets me down to my final product. What questions did you guys have on filling that out? You all did a pretty good job of reasoning your way through what has to happen first. Heat, absolutely. So remember, molecules are never stagnant. They're always moving. And if I can get them to move faster and faster, every now and then they run into something and that energy transfers into a bond breaking. That's essentially what's happening here. I have heated these up. And to be honest, heating them up sometimes is room temperature. That is still a lot more energy than you'd think. Water is playing a role here as the solvent. The partial negative on oxygen can help stabilize that positive on carbon. That just makes it easier for this to happen. It lowers the activation energy. That's all. But it's not playing a role in making or breaking a bond. So I've heated this up enough for the carbon and chlorine to break off from each other. And once that happens, the water is able to bond. Cool. All right, beneath that, we have a couple of other mechanisms. Now you can see that these mechanisms have already had the straight arrows added. So what we're going to do is add the curved arrows to show how electrons need to change. So let's start with our first structure, which is 1-methyl-cyclohexene. And I've shown that it can form 2 different things. This positive charge on the more substituted carbon, or this positive charge on the less substituted carbon when it reacts with an acid. This should remind you a little bit of your midterm question, right? Let's spot the difference. What bonds break during this step? The alkene pi bond breaks, the carbon-carbon pi bond breaks. So I need to have an arrow that starts at the carbon-carbon pi bond. It's not clear, but there is a structure here with Br minus in the intermediate. It's also not clear because it's assumed, but in both of these structures, one of the carbons has taken the hydrogen from my acid. Mechanistically, there is no way to differentiate that. Our mechanism, our curved arrow mechanisms, cannot tell me which of these carbons will use the electrons. I will have an arrow that starts at the bond and points towards the hydrogen. But I can't communicate which of those carbons is doing it, which means these are my 2 possibilities. These electrons are used by the more substituted carbon on top, and they bond to the hydrogen, which means these 2 electrons are lost by the carbon on bottom, or these electrons are used by the carbon on bottom and lost by the carbon on top. Yes, there is, which we see when we see the final product. looks like this. We're going to get into why does the cation form on one carbon over the other. We'll talk about that in section 8. It does, and we'll talk about why. I need another arrow for this step. Yes, from the HBr bond to the bromine. Here's what I would want you to take away from this step. Carbon-carbon bond breaks, carbon-hydrogen bond forms, and hydrogen-bromine bond breaks. Does that mean I need to have 3 arrows? No, because 2 of those things are being described by just 1 arrow. Yes, that is the rule. Bonds break to the more electronegative atom. Bonds form from the more electronegative atom. Carbon bonded to hydrogen. That's because carbon is more electronegative. It has to share its electrons with hydrogen to make that bond. The bond breaks to the bromine. Bromine is more electronegative. It gets control of any of the electrons. Now, we have this 2 possibilities of an intermediate that could form, but based on the final product we see, which intermediate actually forms? The top intermediate. So we're going to ignore this bottom intermediate because based on our final product, it doesn't actually form. How could I know that this is the product that forms and not a structural isomer of this? Put it in the NMR. Look at the hydrogen signals that come out. The hydrogen signals will tell me what my structure looks like, which means that I can verify that this is the structure I get, which means this must be the intermediate that forms for it. If this were the intermediate on the bottom, I'd have a structural isomer. My bromine would bond to a different carbon. That would give me different hydrogen signals. That would give me a different NMR spectrum. So, can you spot the difference from these intermediates to my final product? What bonds need to break? What bonds need to form? Bromine carbon bond breaks, forms. Anything break? So how many arrows do I need? Just 1. Where is it going to start from? From the electron pair on the bromine. Now I could draw in the electron pairs, or that negative charge represents an electron pair. So I can start from that negative charge and I can draw it to the carbon atom. Because when a bond forms, the electrons come from the more electronegative atom. That's the mechanism. All right. Let's look at the next mechanism underneath it. We've got water, tert-butyl bromide. We don't know what the intermediate is, but it's being indicated to us that we do have an intermediate. Once again, I've not really done a good job of telling you what the final products are, so let's fill these in as H3O plus and Br minus. Let's talk about things that need to happen overall. Camilla, you looked really concerned about what you were writing down. You're confused about this, or is my handwriting sloppy there? Where are you getting that third hydrogen from? Good. So let's spot the difference overall. What all needs to happen? In the long run, what do I need to do? break the C-Br bond. Carbon bromine needs to break. What else? Carbon pi bond needs to form. What else? Yeah, CH3 becomes CH2. What does that mean? CH bond needs to break. By the way, I'm not going to be able to show arrows for these bonds breaking unless I show those bonds. And we have agreed with bond line structure that we can assume all of our CH bonds. But if I need to show it breaking, I will not be able to assume it. I will need to explicitly show it so that I can show those electrons doing something. There's one last thing. I have a CH3 that eventually becomes a CH2, so one of those CH bonds must break. What's the last thing? OH bond forms. All right. So let's think a little bit about logistics. What should be plausible first? Bromine leaving makes sense. We've already seen an example. You guys just filled out that reaction coordinate diagram where a halogen left and left behind a carbocation, a carbon with a cation. So we know it's plausible because I've already given it to you and I didn't look surprised at all when you saw it, right? It wouldn't make a lot of sense for me to form the OH bond right away because I know that OH bond forming is coming from the CH bond breaking. These two are connected. And CH, not a very good acid. So it really doesn't make sense for me to start with taking the hydrogen from an atom that is not a good acid. So I think this is something that happens in my second step. This is a term I forgot to give you. The mechanism, the reaction, is made up of elementary steps, things that happen one and then the other. Like an elementary step would be getting out of my PJs. An elementary step is putting on my socks. An elementary step is putting on my shoes. Those are all elementary steps because they happen on their own. These are all elementary steps. Elementary steps are represented by transition states. This has 2 steps. I can't get to my product straight away. There's 2 steps to get there. So I think this makes sense happening in the first step for sure. But then this kind of leaves me with my carbon-carbon double bond. Should that happen in the first step, or should that also happen in the second step? There wouldn't be any electrons to form the carbon-carbon pi bond because those electrons are going to have to come from some other bond breaking. And I know when the carbon-bromine bond breaks to the more electronegative atom, to the bromine. So where am I going to get the electrons to form the carbon-carbon bond? Well, the CH bond breaks to the more electronegative atom, which is carbon. So I can get electrons for my carbon-carbon bond from the CH bond breaking. An OH bond forming, bonds form from the more electronegative atom, which means oxygen will be the one forming this bond. Carbon is the one taking these electrons to form this other bond. So this also has to happen in the second step. Let's walk it out. I don't know why I've never said that before in my life. Let's work it out. Carbon-bromine bond breaks, leaves behind a carbocation and bromide, and I still have water. Okay, one thing is done. My carbon-bromine bond has broken. I'm going to need 3 more things to happen in my second step. How many arrows do you think I'll need? I heard 2 and 3. The question is, can any of these be combined with the same arrow. If carbon is going to take its electrons from hydrogen and also give them to its neighboring carbon, then I can show that in just one arrow. And forming a bond to oxygen, that can be shown in just one arrow. First, I need to show the CH bond. Does it matter which methyl group I pick? They're all identical. So I could really draw it on any of them. Since we know that it's going to have this kind of, we're going to lay it out this way, maybe we show the bond up here. Actually, I'll show it going to the right, just because my water is closer to the right. So you guys okay? I've taken CH3. I've explicitly shown one of the CH bonds, because the other two are not changing. If it helps, draw them all out and just have it be a little bit more cluttered, but know what you're looking at. OH bond forms from the more electronegative atom. Why did I draw a lone pair on? It's not the atom that's attacking, it's the lone pair on the atom that is attacking. If it helps, draw both of oxygen's lone pairs. Only one of them is relevant. If you don't show the lone pairs, and you showed this, it's confusing, because these are electron arrows. You have it starting at an atom. It has to start at electrons. These are the electrons. In my rules, when I have you draw mechanisms, in my rules, I tell you, draw all relevant lone pairs. This is a relevant lone pair because it's being used to form a bond. CH bond breaks. So I have an arrow that starts at the CH bond. Where should it point? I'll have it point to the other carbon so that I can form the carbon-carbon bond. I'll do both of these in just one arrow. 2 arrows. 3 things happened. We saw the same thing here. 3 arrows, 2 arrows, but 3 things happened. I watched a video the other day where I watched somebody like pour out water from a water bottle, and the water was pouring out, and then air was kind of pushing its way back in, and then water pours out and air pushes back in. It gives that bubbling. And I thought about how that could be an analogy here for arrow pushing. If I wanted to show the water coming out and the air going in, no, but I don't have a, I didn't flesh it out. So just know that I thought of another analogy for this, but I haven't figured it out yet. I might come back to it next week. There you go. Jordan. Good. Yes. No. Not, I mean, if the arrow points to a bonding region, if I already have a single bond, and then I have an arrow pointing to that single bond, well, now I'm going to have more bonds there than I did before. That would indicate a pi bond forming. Sorry. I don't know if that answered your question. If an arrow starts at a bond and ends at another bond, yeah, that is a pi bond forming. I'm going to give it to you anyways. Okay, look at what I've put on the top of this. Oh, I didn't put it on canvas yet. What did I put on the top? Spot the difference. What do I mean by spot the difference? This stuff. What changes step by step? What bonds form and what bonds break? Don't do anything else. Just show the change that's happening, right? On the top row, how many steps are these reactions? One step. The top row is a one-step reaction, two different one-step reactions. All of the bonds forming, all of the bonds breaking have to happen at once. Second row, how many steps? Two steps. Two arrows, two steps. Bottom row, how many steps? Three steps, three arrows. Look on the back. How many? 3 steps. So for each elementary step, add the arrows necessary. Spot the difference at that elementary step. Yeah, I'm working on it. If I don't do it now, I'll forget forever. I had an activity, but we've got 5 minutes, so I really don't know that we've got the time to go through this activity, because it takes like 10 minutes at least. And we're gonna be learning remotely next week. We're gonna be on Zoom. So I don't know that we'll be able to do this activity next week either. I think I have part of it recorded on last semester's recording, so you'd be able to kind of go through the activity the way that they did, but it's really not the same. Essentially, this activity is just, I give you intermediates that don't exist and intermediates that do exist, and I have you try to figure out what intermediates make sense in a logical pathway to get from starting material to end. I think we'll have to skip over it this semester. Work on this worksheet over the weekend. If you want to spend a few minutes starting on those one-step problems, feel free to. The backside has radicals involved, which is a little bit more complicated in terms of using arrows. And when we get on Zoom Monday next week, we'll start by going over some of these problems and just getting you familiar with arrow pushing, spotting the difference. Because then by the end of this unit, you will not be given the intermediates. You will need to know what intermediates to predict and how to draw the arrow pushing. So this is kind of scaffolded. I'm giving you tons of intermediates. I'm having you get used to drawing the arrow pushing. And in a few weeks, you will need to know the intermediates as well. All right? So we'll work on this on Monday over Zoom, and we'll talk about alkene nomenclature and alkene reactivity on Monday as well. If you want to stick around, I'm happy to give you some feedback on this. Otherwise, I'm posting it right now to the Unit 4. All right, it is now uploaded under organic reactions. It's called Practice Mechanisms. You're welcome. Have a good weekend, guys. I'll see you virtually next week. Thanks.